Could we have the screen? Yeah, thanks. Let's wait for it. So, by the way, you can use this clip-on microphone if you want.
I think it seems to be okay as long as people stand.
Yeah, as long as you're standing, like, yeah, it seems to work. Okay. That's working. This is thanks to Nabil.
I think the mouse pointer is better.
Sorry?
The mouse pointer is better pointed than that tiny red.
Yeah, I think so. Depends how you feel about getting stuck there. Okay, so we are slightly late for the last session before lunch, but we're very happy to have Harvey Reall telling us about the second law of black hole mechanics in effective field theory.
Okay, well, thank you for the invitation to speak here. Thank you for Prem and Carlos for organising this nice meeting. So I'm going to speak about work I did recently with Stefan Hollands and Aron Kovacs, which is summarised in this paper from a few months ago. So I'll be speaking about black hole mechanics. So let me first remind you what that is. So the usual laws of black hole mechanics are a set of laws in classical general relativity coupled to matter fields obeying suitable energy conditions. So, for example, the first law of black hole mechanics governs linear perturbations of a time-independent black hole. So if you perturb such a black hole, then the change in its mass will be related to the change of in its entropy and its angular momentum by this formula, where T is the Hawking temperature and omega is the angular velocity of the black hole. So the Hawking temperature is given in terms of the surface gravity of the black hole by Hawking's famous formula. And in standard GR, the entropy of a black hole is given by the Bekenstein-Hawking formula in terms of the horizon area A. So this is standard GR, but about 30 years ago, Bob Wold showed that this first law of black hole mechanics actually holds in a much larger class of theories. So he considered a class of theories arising from a diffeomorphism invariant Lagrangian, and showed that for any such theory, you can prove a first law of black hole mechanics of this form for a suitable definition of the entropy S. So the kinds of theories that we're talking about are theories containing high derivative terms in the Lagrangian. So I was told to make this talk accessible to string theorists, so I'll say that these terms could be alpha prime terms coming from string theory. So anyway, but it could be completely unrelated to string theory. So all we're using is diffeomorphism invariance of the Lagrangian. So this gives a definition of black hole entropy, generalizing the Bekenstein-Hawking result, that applies to any stationary black hole. So stationary in GR means time independent. So we have a definition of entropy for any time independent black hole in a theory of this type, and this is the famous Wald entropy. So this was the first law of black hole mechanics. So in this talk, I'm going to ask not about the first law, but the second law. So the second law is in standard GR is the Hawking area theorem, which says that the area can only increase under time evolution. So the question is, can we find a definition of the entropy for a dynamical, in other words, a time-dependent black hole, that obeys a second law, in other words, it increases in time, and it agrees with the Wald entropy for a time-independent black hole. Okay, so that's the basic question I want to discuss. And of course, this is something people have thought about for some time. Back in 1994, Aron Reall proposed a definition for the entropy of a dynamical black hole for theories of this type. Let me give you an example. I'm not going to just give the details of their definition, I'll just give you an example. So let's consider Einstein-Gauss-Bonnet theory, which has this Lagrangian here. So we have the usual cosmological constant, Einstein-Hilbert term, and then we add a four derivative term proportional to the Gauss-Bonnet, the Euler density associated with the Gauss-Bonnet invariant. So that's just this term quadratic in curvature. So this is topological in 4 dimensions, but not in higher dimensions. So let's imagine we're doing this in high dimensions. And then the Aron-Reall definition gives you a formula for the entropy of the black hole. So if you have a cross-section C of the event horizon, then the formula looks like this. So the first term here is just the Bekenstein-Hawking result, and then we're adding a term here, R of C, where R is the Ricci scalar of the horizon cross-section. So that's an example of what the Aron-Reall entropy looks like for this particular theory. So if we return to the general case, then Aron-Reall showed that their definition has various nice features. So it's free of certain ambiguities that can affect the covariant phase space formalism on which this is based. It agrees with the Reall entropy for a stationary black hole, and it satisfies the first law. But it's not clear, and Aron-Reall just left this as an open question, whether it satisfies a second law. In other words, does this definition give us an entropy which increases under time evolution? Shortly after, there was work by Jacobson, Kang, and Myers, who looked at a very special class of theories. So these are the so-called F of R theories. So these are theories for which the Lagrangian is a function only of the Ricci scalar. And in that case, they were able to prove a second law for a certain definition of the entropy. But the entropy for which they prove a second law is not the Aron-Reall entropy. It's a different entropy. So that maybe is an indication that the Aron-Reall entropy is not going to work out. But we'll see it still plays an important role. So that was the mid-90s. So we can then... Okay, before we come up to date, let me just say one more thing. So in this talk, I'm not going to solve this problem in full generality. What we're going to be considering is the second law perturbatively around a stationary black hole. So the idea is we have some stationary black hole and we perturb it, and we ask whether that perturbed black hole satisfies a second law. Yeah, Ami?
What is the notion of an entropy? Defining entropy is anything that can count as freedom?
No, because this is all classical. We're not doing statistical mechanics here. So we're doing it in the sense, we're looking for some local geometrical quantity associated with the event horizon, such that under time evolution that quantity cannot decrease. So that's basically the goal. The question of how it's related to some microscopic degrees of freedom is obviously very interesting, but that's way beyond the scope of this talk. So we're going to consider the second law perturbatively. So we imagine we have some time-independent black hole described by the metric G bar, and then we're going to perturb that metric, and we're going to ask whether the perturbed black hole satisfies, or can we find a definition of entropy in this perturbative setting that satisfies the second law. And we're going to, so epsilon here is some small parameters, so we've got some first order perturbation, some second order perturbation, and so on. And the idea to keep in mind here is the physical situation we're interested in is a black hole which is settling down to equilibrium. So we're not going to be describing anything like a violent process like a black hole merger. It's really the late time settling down to equilibrium phase of black hole evolution that we'll be discussing. Now, if you treat high derivative terms in the sense of effective field theory, which is what we'll be doing in a moment, then this does seem to be the optimal situation in which high derivatives may play an important role. And that's simply because in a violent event like a black hole merger, just the usual area increase you get from Bekenstein-Hawking is going to just swamp anything you get from higher derivatives. And so this process where you're settling down to equilibrium, where the area increase from Bekenstein-Hawking is small, seems to be the optimal situation in which the higher derivatives might play an important role. Okay, so jumping forward to more recent times, so some progress on this problem was made 7 years ago by Aron Wall. So what he did was to describe a procedure or an algorithm where if you're given a theory of this type, some diffeomorphism invariant Lagrangian, he gives a procedure for defining an entropy which satisfies a second law to linear order in perturbations around a stationary black hole, so to order epsilon in this formula. His procedure, it turns out, produces a result for the entropy which adds certain terms to the Iyer-Wald entropy, which I mentioned earlier. And so therefore we decided to call the result of this procedure the Iyer-Wald Wall entropy. I don't know whether any of those three people would actually be happy with that terminology, but that's what we called it in our paper. So the simplest kinds of terms that the Wall process adds to the Iyer-Wald entropy are of this kind of form, so this is schematic. So if we have a cut of the event horizon, so cross-section through the event horizon, then you can consider the light rays which are orthogonal to that cut. So you have outgoing light rays which propagate along the event horizon, and then you have ingoing light rays which fall into the black hole. And those light rays have expansion and shear, which are described by certain matrices which we call K and K bar. And so the simplest kind of Wall terms are basically products of K and K bar. So there are two possible terms you could write, which are just involve K and K bar, because there are two ways of contracting the indices here. But there could be much more complicated terms where you also have the Riemann tensor multiplying, things like this. So as an example, if you look at Einstein-Gauss-Bonnet theory, as I mentioned earlier, this is an interesting special case in the sense that if you work through this procedure for Einstein-Gauss-Bonnet theory, you find that these terms which generically are present turn out to be absent for Einstein-Gauss-Bonnet. So for Einstein-Gauss-Bonnet, the Iyer-Wald Wall entropy is the same thing as the Iyer-Wald entropy. Now, as I said, this produces a entropy which satisfies a second law to linear order. But to linear order, the second law actually says that the entropy does not change. And it's easy. So here, S dot is the rate of change of the entropy with respect to some coordinate along the horizon. Delta S dot is its first variation. The reason it can't change is that, imagine it did change, and let's say it increased. Well, then, to linear order, you could just flip the sign of the perturbation, and then you'd get an entropy which decreases, which would violate the second law. So therefore, to linear order, the second law simply says that the entropy cannot change. And so that's what the Wall prescription does. It produces an entropy with that property. But if you really want to see an entropy increase, then you need to go beyond linear order, and we need to work to quadratic order in perturbations around a stationary black hole. And that's essentially what we will be doing. Just as a footnote, really, Wall also considered the case where he separates the fields into gravity plus matter, and he assumes that the matter fields are described by some energy momentum tensor satisfying the null energy condition. If you do that, then you can get an entropy increase, which is driven entirely by the matter fields. But that seems a little bit unsatisfactory in the sense that it's not treating the matter fields using the same linearized approximation that you're applying to the metric. And also, there's no reason, when you consider higher derivatives, that the null energy conditions would be satisfied by the matter fields. So we won't be doing that either. Well, this would then agree with the Jacobson-Kang-Myers entropy to linear order, basically. I mean, yeah. Okay, there's a variational way of looking at this, which we found quite interesting. This isn't essential for understanding the rest of this talk, but imagine that we have a theory that does admit an entropy S which satisfies the second law, so it's non-decreasing. And let's now look at a stationary black hole. So if we have a time-independent black hole, then the entropy is not changing. It has S dot equal to 0 on any horizon cross-section. And therefore, a stationary black hole minimizes S dot, because if S dot is always positive, stationary black hole is S dot equal to 0. It therefore minimizes S dot within the space of horizon cross-sections, whatever that is. I won't attempt to define it. So at least heuristically, a necessary condition for a second order hold is that if we perturb a stationary black hole, it must satisfy the conditions to be a minimum. So the first variation must be 0, and the second variation must be positive. And as we've seen, that this first condition, that the first variation is 0, is indeed what we get from the Iyer-Wald wall entropy. So a stationary black hole does indeed extremize S dot, if we take S to be the Iyer-Wald wall entropy. But we don't know about this second condition. This extremum may not be a minimum. It may simply be a saddle. And in fact, generically, that's what happens. Okay. Any more questions at this stage? Okay, so let me come to what we've done. So the new thing in what we've done compared to previous work in this area is to work consistently within the framework of effective field theory. So for simplicity in this talk, I'm just going to consider the effective field theory of vacuum gravity, although we do discuss matter in our paper. So if we're looking at the EFT of vacuum gravity, then we'd write down the Lagrangian, which is the usual cosmological constant, the Einstein-Hilbert terms, and then we add higher derivative terms ordered by increasing numbers of derivatives. So we have 4 derivative terms which are quadratic in the curvature tensors, so Ricci scalar, Ricci tensor, and then this Gauss-Bonnet term I wrote down earlier. And then there'll be 6 derivative terms, 8 derivatives, and so on. And we're going to assume that the coefficients of these terms are all given by appropriate powers of some length scale L, which we call a UV length scale. And so in effective field theory, this would be characteristic of the UV scale at which this theory would break down, and you have to move to a more fundamental description. And so these A's would then just be dimensionless coefficients. Okay, so this L will be playing an important role in our discussion. So if we view so the work of Iyer-Wald and also Wall essentially works for any diffeomorphism invariant Lagrangian. It doesn't have to be treated as an effective field theory. You could say this is the fundamental theory of gravity and work with it. But we're going to view the theory as an effective field theory, and this restricts the scope of the second law in 2 important ways. So firstly is that we have to remain within the regime of validity of effective field theory. So when we start introducing higher derivative terms into equations of motion, then those equations of motion, it's well known, admit various solutions with pathological behavior. They might have high frequency oscillations or exponential growth and so on. These are unphysical solutions, okay? And since they're unphysical, there's no reason why we should care about them when we satisfy the second law. So we're not going to try proving a second law that holds for arbitrary solutions of these theories because we don't care about the unphysical solutions. And indeed, there's no reason why they should satisfy a second law. They're unphysical. So we're only going to consider solutions lying within the regime of validity of effective field theory. And what we mean by that is if I define capital L to be the smallest length or time scale over which the solution varies, so this could be, for example, the size of the black hole, or it could be dynamical time scales associated with quasi-normal modes, anything like that, we're assuming that big L is much larger than little l. So the solution is varying over a length which is large compared to the UV length scales. And so this means that we would expect, if this is true, that terms with increasing numbers of derivatives are successively less important. So that's the starting point. Notice I should emphasize we do not assume that our solution is constructed by an expansion in this parameter, little l over big L, this small parameter, which one could try to do, but in a time-dependent situation that approach is problematic because you can get secular growth, you can get terms growing in time in this kind of expansion. So we won't be doing that. So let's say in general, we're not going to know an effective field theory exactly. You're only going to know the first few terms in the Lagrangian. So let's say we know our effective field theory, we know all the terms up to n derivatives. And that means we can write the effective field theory equation of motion like this. So E mu nu here is all of the terms in the equation of motion up to n derivatives. So the usual terms from GR, 2 derivative terms, then we'd add 4 derivative terms, all the way up to the n derivative terms that we know. And on the right-hand side, we're going to have a contribution from the terms we don't know, the terms with more than n derivatives. Okay, and these are going to come with a coefficient of order L to the n. So when I write the order L to the n, what I should really be writing is order little l to the n over big L to the n plus 2, where this big L is this L. But it's a bit inconvenient to have to keep writing that everywhere. So I'm going to suppress these big L's everywhere. But when you see little l to the n, just put the big L's back in by dimensional analysis. Okay, so that's the EFT equation of motion. Yeah. I'm not saying it's not consistent, and certainly you can try to build solutions that way, but what can happen, particularly in a time-dependent situation, is that the coefficients in that expansion could grow in time. They could be like polynomial growth in time is a simple way of seeing this is if let's imagine you have a quasi-normal mode, so you have exponential you have oscillations or exponential decay or something like that, and let's imagine the higher derivatives correct the frequency of the quasi-normal mode. Okay, if you now then Taylor expand that in that correction, you're Taylor expanding this exponential times with a time in the exponent, and that will generate factors of t in your expansion. And so your expansion is badly behaved at large t, basically. That's the problem. So, but as I said, we don't actually ever have to solve the equations, so we're not going to have to do that, okay? Well, if they don't exhibit this bad growth, yeah, but in general, I think you are going to always see this. Particularly if it's not time dependent, you may be able to get away with this. But in a time dependent problem, it's much harder. Okay, so here's our EFT equation of motion again. The first left-hand side contains the terms up to n derivatives. The right-hand side is the stuff with more than n derivatives that we don't know. So the idea now, the second main idea is that if we consider the theory defined by the left-hand side, in other words, by the terms up to n derivatives, we're not going to try and prove a second law that holds exactly for this theory, because we recognize that this theory is not an exact theory. It's only a theory up to corrections of this order. So we should only aim to prove a second law that holds to the same order of accuracy as the theory itself. In other words, modulo terms of order L to the n. Okay, so that's what we're going to be doing. So the goal is that from the terms with up to n derivatives, we want to construct an entropy which is increasing modulo possible terms of this size. In other words, it's bounded below by something which is possibly negative, but if it's negative, it can't be too negative. It can only be of the same size as the unknown terms we don't know when we've truncated our effective field theory. So in particular, if we increase n, if we increase the number of derivatives to which we know our effective field theory, then we will increase the accuracy to which the second law is satisfied. So I think that's the optimal thing you could expect in EFT for proving a second law. And so basically what we do in our paper is we show how to do this, how to define an entropy that achieves this to quadratic order in perturbations of a stationary black hole. In other words, to order epsilon squared in this kind of amplitude expansion around the stationary black hole. Okay, so the second variation of S dot is bounded below by terms of this size. So it satisfies the second law modulo terms of the same size as things we've neglected when we truncate our EFT. And the way we do this is we take the Iyer-Wald wall entropy and we add new stuff to it, basically. And so we have to add new stuff to it in an appropriate way in order to achieve this goal.
Now that's 4.
Say that again?
The last line, that's 4.
That last line is...
N is now 4.
No. So quadratic order, there are two things going on here. N is the number of derivatives to which we understand to which we know our effective field theory. That can be anything. Quadratic order means quadratic order in the amplitude of perturbations. Yeah, it's important to emphasize that point. Yeah, so we're doing two things. We've got this number of derivatives to which we understand our theory, but we're also then doing perturbations around a stationary black hole, and we're working to quadratic order in the amplitude of those perturbations. Okay. So before I explain how we do this, let me yeah. I'm going to just comment on that towards the end of the talk. So yeah, I'll say something. The short answer is we don't know, but I will say some words about that at the end. So let me say a bit more about what we produce from this procedure. So in equilibrium, our entropy agrees with the Wold entropy, which is good. And to linear order in perturbations, it agrees with the Wold-Wall entropy. That's because we're adding things which are quadratic. And therefore, it also satisfies the first law. So it satisfies the basic things you would need your entropy to satisfy. Now, if we're working with equations of motion where we've retained terms up to n derivatives, then the entropy is not too hard to see. Will contain up to n minus 2 derivatives. So standard GR, you have 2 derivatives. The entropy contains 0 derivatives. It's just the area. Now, the new terms that we're adding to the entropy always involve at least 4 derivatives. So they only appear when n minus 2 is at least 4. In other words, when n is at least 6. Okay, so we need at least 6 derivatives to see our new terms in the entropy. If we only look at the leading higher derivative corrections to Einstein gravity, these are 4 derivative terms, so they have n equal to 4. And for these corrections, our result therefore implies that the Wold-Wall entropy, without any modification, already satisfies the second law to quadratic order in this sense of effective field theory that I've described. But if you go beyond 4 derivatives, then our approach will give new terms. So here's an example of how this works. So here's our formula. Second variation of the rate of entropy increase is bounded below. Let's say we take Einstein-Gauss-Bonnet theory, as I described earlier. Here it is again. And let's now do something very strange. Okay, let's view this theory as an effective field theory for which we know that all of the coefficients of all of the higher derivative terms I've not written are all exactly 0. Okay, it's a very strange thing to do, but we're free to do it. Okay, so let's do that and work out what the entropy is for that effective field theory. So if we consider a cross-section C of the event horizon, let me define little s to be, little s over 4g to be the entropy density. In other words, if we integrate this, we get the entropy. And let's ask, what does this look like as we increase the number of derivatives to which we trust this theory? So if we trust this theory up to 2 derivatives, that means we're just doing standard GR. We just got the Einstein-Hilbert result, Einstein-Hilbert-Lagrangian, and then the entropy is just the Bekenstein-Hawking entropy. So S equal to 1, we integrate that, we get the horizon area. So for n equal to 2, this just gives us Bekenstein-Hawking, which will satisfy the second law modulo terms of order L squared coming from the higher derivatives. Let's now say we trust this as an effective field theory up to 4 derivatives. So we include this Gauss-Bonnet term. So up to 4 derivatives, I told you that our procedure doesn't produce any new terms, and so in this case we just get the Wold-Wall entropy, which looks like this. Remember, R of C is the Ricci scalar of the horizon cross-section. But now let's say we actually trust this theory up to 6 derivatives. In other words, the coefficients of the 6 derivative terms really is 0. Okay, well, it's a weird thing to assume, but we can assume it, and now work out what is the next term in the entropy. And this is something my student Ian Davis has been working out. And after some heroic computer algebra calculations, he's done it. And so we have these matrices K and K bar describing the expansion and shear of the ingoing and outgoing null geodesics, orthogonal to this cross-section C. And so the new terms are quadratic in K and quadratic in K bar. Remember, these are matrices, so there are lots of different ways of contracting the indices here. So I think there are 8 or 9 different terms in this that I've written here. Notice that you might have expected K bar terms to appear at n equal to 4, but as I mentioned earlier, Einstein-Gauss-Bonnet is special. Those terms do not appear for Einstein-Gauss-Bonnet, but generically you would expect to see them in a 4-derivative theory. Okay, so that's the end of kind of the overview part of my talk. So the rest of the talk I'll be giving you a little bit more of the details of how this works. So does anyone have any questions at this stage? Yes, Samir. Mm-hmm. I'll mention field redefinitions at the end. Yeah, it's an interesting question. In fact, it relates to Tim's question. I'll say something about that at the end, yeah. But you're right, if we're doing 4 derivatives, if we can get rid of all the 4 derivative terms except this one using a field redefinition, which is why this one is perhaps the most interesting. Okay, so let me tell you a little bit about how we do this. So we have some assumptions. So the main assumptions we're making is that we have a black hole space-time with a smooth horizon. that is settling down to equilibrium at late time. So it's settling down at late time to a stationary, time-independent black hole. So with these assumptions, we can introduce a nice set of coordinates, so-called Gaussian null coordinates. Maybe I'll go over to the board. So this is the event horizon, this is the line here. Take some cross-section through the event horizon, we can introduce coordinates xa on that cross-section, so it's a b minus 2 dimensional manifold. We then have v being the affine parameter along the horizon generator, so let's move along the horizon. And then we shoot null geodesics off the horizon in this direction, and r here is the affine parameter along those null geodesics. So this gives us a set of coordinates where the horizon is r equal to 0, and to work out what the metric looks like in these coordinates, it looks like this, where you see there's a coefficient alpha here, there's some beta here, and there's mu here. So mu here is basically the metric on cross-sections like this through the horizon. So these are the coordinates that we use. In fact, this is very similar to what Aron Reall did in his work. For a metric of this type, there's a scaling you can perform where you rescale v and r by some constant a. If you do the scaling like this, then the form of the metric will be preserved. And it's convenient to classify various objects according to how they transform under such a scaling. So if you pick up a factor of a to the power b, then we say that a certain quantity, if it picks up a factor a to the power b under a boost, we say that that quantity has boost weight b. Okay, so this boost weight is an important idea. So alpha, beta, and mu, the metric components, all have boost weight 0. But these matrices k and k bar I've been discussing, in these coordinates, k is just the b derivative of mu, k bar is just the r derivative of mu. This is boost weight 1, this is boost weight minus 1. So importantly, it turns out that if you look at a stationary black hole, all positive boost weight quantities vanish on the event horizon of a stationary black hole. And that's going to be important because at late time, we're assuming that everything's settling down to a stationary black hole, and so at late time, positive boost weight quantities are going to vanish. So let me just remind you of how the usual proof of the second law works. So this is just the usual proof from GR. So in GR, we're looking at the horizon area. If you calculate the rate of change of the horizon area with respect to this coordinate v along the horizon, then that rate of change gives you the trace of this matrix K, which is the expansion of the horizon generators. So that's the rate of increase. So the goal is to prove that this trace of K is something which is non-negative. And we do that using the Rayleigh-Drury equation. So the Rayleigh-Drury equation is just work out the VV component of the Ricci tensor in those coordinates, and that's what you get this equation. So if we now assume that the Ricci tensor, the VV component, is bounded below, this is called the null convergence condition. So this will be true if we coupled gravity to matter through the Einstein equation and the matter obeyed the null energy condition, then this will be true. Then you can see that the right-hand side here has a sign. It's negative, and so we see that the trace of V is therefore a decreasing function. But at late time, because this is a boost weight 1 quantity, it vanishes. So we have a decreasing quantity which vanishes at late time, and therefore the trace of K must be positive, and therefore A dot must be positive. So that's how the area law works out in standard GR. If we now go beyond standard GR and we look at a higher derivative theory, then it's no longer true that the Ricci tensor will obey this null convergence condition. So the Einstein equation will now tell us that RVV is something coming from the higher derivative, something of order L squared, and that doesn't necessarily have a good sign. Now you might say that, well, when effective field theory is valid, we might expect that this KK term, which is just a standard GR term, is going to dominate any contribution coming from higher derivatives, because, of course, we're assuming the higher derivatives are small in some sense. However, that's not always going to be the case. There are always going to be some situations where K just happens to be small somewhere on the horizon. If K is small somewhere, there's no reason why terms coming from RVV, things like this, so this is the V derivative of that beta in the metric over there, or something like a transverse derivative of K, These may well overwhelm this first term on the right-hand side of Ray-Chuduri, and you can get a possible horizon decrease. So that's why this is non-trivial, essentially, that even within the regime of validity of effective field theory, it's not obvious that you have a second law. So what do we do? Our approach is formulated in terms of an entropy current, which is a vector field defined on the event horizon. So on the horizon, we have coordinates v and x. So we have a vector field with components SV and SA. You can think of SV as the entropy density. And for standard GR, SV is just 1 and SA is 0. So the entropy of a horizon cross-section is defined as the integral of SV, since SV is the entropy density. Okay. We introduce some notation here. We define what we call the divergence of the entropy current as follows. So here we've basically got a time derivative of SV. Mu is that metric appearing on the horizon cross-sections. And D here is the covariant derivative defined by this metric mu on the horizon cross-section. So it's a metric on the spatial cross-sections of the horizon. Okay. So this is just notation. For standard GR, just for orientation, this would be the trace of K that I was talking about earlier. It would be just the expansion of the horizon generators. So if we now look at the rate of increase of the entropy, so we take a V derivative of this equation here, and we can use this definition of the entropy, divergence of the entropy current. This term is a total derivative, so when I integrate over the horizon, it drops out, and I can relate S dot to this divergence. Okay. So if we were to copy the usual GR strategy, our aim now would be to show that this quantity, the divergence of the entropy current, is a decreasing quantity. Our late time equilibrium assumption would give us that quantity tends to 0, and therefore decreasing and tending to 0, we could deduce that it had to be positive, and hence this whole thing would be positive, and we'd be done. But unfortunately, that does not work. Okay, it's not true that this equation, well, in our approach, we don't ever get an equation of this form. Okay. So we have to do something a bit different. So let me tell you a little bit more about the structure of this, the kind of equation we're working with. So this entropy current is useful even in Aron Wall's approach. So in the Aron Wall approach to entropy, let's say we have the equation of motion E mu nu equal to 0, where E mu nu contains all these high derivative terms. What you can show is that Wall's algorithm is essentially equivalent to the statement that there exists an entropy current satisfying this equation. So on the left-hand side, we get the rate of change of the divergence of the entropy current. Then we get EVV, and then we get something which is quadratic or higher order in positive boost weight quantities. So remember, the positive boost weight quantities vanish for a stationary black hole. And so this is a generalization of Ray-Chuduri's equation. In Ray-Chuduri's equation, this on the left-hand side, you just get the expansion of the horizon generators. This would be RVV, and this would be K squared. So with higher derivatives, this F is much more complicated typically, but it contains the usual K squared term. So this is a generalization of the Ray-Chuduri equation. And basically, our work, the main achievement of our work is to show that this F, this thing which is of quadratic order in positive boost weight quantities, can be rearranged in a nice way at the expense of A, going on shell, so we have to use all of the equations of motion, and B, invoking effective field theory, which was not required for Aron Wall's approach. So, how does this work? So let's assume, as I've been describing, that we know the EFT equations of motion up to n derivatives. So E mu nu contains the terms up to n derivatives. The right-hand side is terms with more than n derivatives that we don't know. So basically working order by order in derivatives, so we have an inductive argument, order by order in the number of derivatives, and using the equations of motion at each order, what we show is that new terms can be added to the entropy density of the Aron Wall approach to generate an improved entropy density, which we call capital S, and an associated entropy current, which satisfies this equation. Okay, so this equation, if you compare it with what we had before, it looks very similar. On the left-hand side, we get the rate of change of the divergence of the entropy current. But now we've shown that the terms on the right-hand side have a definite structure. Okay, so we get something which is, there's this usual k squared piece that we get from GR, but that's now corrected by adding some quantity x, which I won't attempt to define, but it arises from the higher derivative terms, in such a way that this first term here is a square of something. It has a sign. We get another term here involving something we call y. This has a particular structure as well. It's a divergence. Okay, so we get a square and a divergence on the right-hand side. And then we get terms coming from the higher derivative corrections we don't know on the right-hand side. Importantly, the new terms that we add to the density, entropy density, are quadratic in positive boost weight quantities, which means that they're quadratic in the amplitude of the perturbation around a stationary black hole. And similarly for this y. So as an example of how we're using equations of motion in this approach, when you work out this f thing on the right-hand side, this is coming from all the higher derivative terms. So there are things like the v derivative of beta. So beta is one of the metric components. That appears on the right-hand side typically, and you have to be able to control that. How do you control it? Well, you can do it first. You can relate the v derivative of beta to the Ricci tensor. So there's some other stuff here which is manageable. So you can write things involving the Ricci tensor, and then you can use the equation of motion to replace the Ricci tensor and push. And when you do that, you're pushing things to higher order in L, basically. So that's basically the strategy. There are problem terms like this, but at each order you can use equations of motion to eliminate those terms and push them to higher order in L, and eventually they reach this order, at which point you don't care about them anymore. Okay, so now if we assume that, so here's our equation again, if we assume that everything is settling down to equilibrium at late time, then the divergence of the entropy current will vanish at late time. That's because it is boost rate 1. So if we integrate this equation with respect to V, then we get a formula for the divergence of the entropy current at time V0. It's just the integral of the right-hand side. And now finally, we can work out the rate of change of the entropy by integrating this over a cross-section of the horizon, a constant V, which gives us this formula. So first we integrate over V, and then we integrate over a horizon cross-section. And this is almost there. I mean, this first term on the right-hand side is positive definite, and so that's clearly giving us a positive contribution to the rate of entropy increase. But then we've still got this term involving this divergence of Y. Okay, and that kind of looks like something which we should be possible to integrate away because it's a divergence, but we can only integrate it away if this D is a covariant derivative with respect to the metric mu defined at the same time as we're integrating over here. And it's not. This D lives at time V primed. Here the integral is at time V0. Okay, so we can't just throw that term away. However, if we're working to quadratic order in perturbations, I told you earlier that Y is quadratic order. So to quadratic order, and only to quadratic order, we can evaluate this in the background geometry, which is time independent, and then it's fine to throw away that divergence. So to quadratic order, what this means is we get an entropy which satisfies the second law, modulo terms of the same order as the terms we neglected when we truncated our effective field theory. So the second law holds to quadratic order in this EFT sense. Okay, so this was for vacuum gravity. If you want to include matter fields, then you have to start decomposing matter fields in these coordinates and understanding what kinds of terms they generate on the right-hand side of this generalized Ray-Chuduri equation. Basically, the goal there would be to assume if you have matter fields for which the two derivative part of the action satisfies the null energy condition, then our expectation is that you can use those two derivative terms to help control the behavior of the high derivative terms in order to get some generalization of this equation where you get another positive term on the right-hand side coming from the matter fields. And so we showed that this works out for the most simple kind of matter field, which would be a scalar field. So if you consider the effective field theory of gravity plus a scalar, we showed that all of this still works out, and I'd expect it to work also for Maxwell fields or more complicated matter fields. Okay, so let me end with a couple of open issues. So one is gauge invariance. So in this approach, what we establish is an entropy which, if we define it on constant V cuts of the horizon, so remember V is that coordinate, the affine parameter along the horizon generators, then we get something which is monotonically increasing in V. But let's say we have two cuts of the horizon which are not surfaces of constant v. We have a cut c at some time and then a cut c primed at some later time, but let's say that c primed is not a surface of constant v. How can we compare the entropies of these two surfaces? Well, we can always arrange things so that they are cuts of constant v. So we can always choose to measure v starting on our initial cross-section c, and then one can always rescale the affine parameter along the horizon generators in a way which depends on x to make c primed also into a cut of constant v. Okay? And then our result implies that S of c, the entropy of c primed, is greater than the entropy of c, at least a quadratic order. However, when we do this, we need to check that the entropy, our definition of the entropy of c, is in fact gauge invariant under this kind of rescaling of the affine parameter. Because if it's not gauge invariant, then our definition for the entropy of c is going to depend on our choice of c primed, which is clearly unsatisfactory. And in fact, this is an issue even for the Ayer-Wald-Wall entropy, so even for the Aron-Wall approach. In that case, with quite a lot of work, we managed to prove that the Ayer-Wald-Wall entropy is in fact gauge invariant under this kind of rescaling of the affine parameter. And as I said, for n equal to 4, so theories with up to 4 derivatives, I told you that our entropy agrees with the Ayer-Wald-Wall entropy. And so our entropy is also gauge invariant for theories with up to 4 derivatives. But what about more generally? Well, if you're working in vacuum gravity, you can just try and classify possible terms that could appear in the entropy. And it's fairly easy to see that gauge non-invariant terms in the entropy can't occur for n less than 8. So you'd have to go out to theories with 8 or more derivatives for this to become an issue. So it's certainly not something that's going to affect the leading corrections or even the next to leading corrections to Einstein gravity. And this is something we're investigating at the moment, whether or not this is actually true. Do these terms appear or do they not appear? So that's future work. Okay, so now let's come back to this other issue, which there are a couple of questions about, which is concerning field redefinitions and uniqueness. So our definition of dynamical black hole entropy looks like it's not invariant under effective field theory field redefinitions. And I mean, a simple way of seeing that is to take just to start with just standard Einstein gravity and perform a field redefinition which introduces R squared terms into the action. If you do that, it appears that the entropy after the field redefinition is not going to be the same as the entropy before the field redefinition. Okay. So the question is this a problem? So it's rather reminiscent of what happens in other areas of physics. So defining what we mean by thermodynamic entropy away from equilibrium, which is basically what we're trying to do, is a notoriously tricky subject. It's something that's been investigated quite a lot 15 years ago or so in the case of relativistic viscous fluids. So Shiraz Minwala's group has done a lot of work on this. And so the idea there is to try and construct an entropy current for a relativistic viscous fluid such that it satisfies the second law. And so in particular, the work of Bhattacharya has shown that the result of that is not unique. Okay, so there are multi-parameter families of entropy currents for a relativistic viscous fluid, which all satisfy the second law. Okay, so what seems likely to me is that this issue of non-invariance under field redefinitions is probably related to this non-uniqueness of the entropy. So the entropy is not unique, and these field redefinitions are just mapping between different possible definitions of the entropy, each of which satisfies a second law, each of which will also satisfy a first law, each of which agrees with the Wald entropy in equilibrium. And so I think it's just another example of non-uniqueness of entropy outside of equilibrium. But anyway, this is something that also needs to be understood much better. Okay, so to finish, the main point is we've introduced a procedure for defining black hole entropy out of equilibrium such that the second law is satisfied to quadratic order in perturbations around a stationary black hole in this sense of effective field theory. So various things to do for future work. So working out examples is the main one. As I said, the new terms that we have in the entropy only appear once you start considering theories with 6 or more derivatives. And so at the moment we're working out examples of what those terms look like. Generalizing our arguments to include different types of matter fields is interesting, and hopefully that's something that we'll also start thinking about. I've mentioned the issue of gauge invariance. At the moment we're just trying to work out some examples to see whether or not they are gauge invariant, and if they are, we'll try and understand why they are, and if they're not, then we've answered that question. There's an interesting sort of similarity with what we're doing and the kind of things people are doing in the fluid gravity correspondence, so it would be interesting to try and tie those approaches together perhaps in some way. And then finally, as I've said, everything we've done is to quadratic order in perturbations around a stationary black hole. And so clearly it's of interest to go beyond quadratic order, although there I think some new ideas are going to be required. Okay, thank you for your attention. Is there a general formula, did you say? No, it's kind of similar to what Aaron Wall does in the sense that he gives an algorithm. Well, you give him a theory, he gives you an algorithm which generates an entropy. And our algorithm lives on top of his algorithm to some extent. So, yeah, so it's in a sense, it is something that you might hope to automate using computer algebra, right? That's sort of what my student is trying to do at the moment, is you give him the theory and his computer algebra will produce the entropy for you, but it's quite complicated.
You can just apply this to Einstein gravity, because there are time-dependent solutions in Einstein gravity.
Well, in Einstein gravity, you just recover the Bekenstein-Hawking entropy, so there's nothing new there.
I mean, there are time-dependent solutions, so what would be the entropy?
The area. I mean, just the usual.
Just the area.
Yeah. I mean, for Einstein gravity, this just gives the usual thing, right? There's nothing new there. Yeah.
In your opinion, the space of all possible entropy functions, is it finite dimensional or rather functional degrees of freedom?
The analogy with fluid dynamics would suggest it's probably finite dimensional, but I'm not certain about that. I would guess finite dimensional, but I'm not. Yeah, it's certainly something that needs much more close investigation. Yeah.
So you said these k-squared corrections vanish for Gaussian due to that order.
Mm-hmm.
Is there a geometric understanding of what arbitrary variates to their corrections?
So for Gauss-Bonnet, you can sort of, there's a hand-waving way of understanding it, which is to go back to, where is it? This kind of equation. So if we had a k-squared term in S, so k already involves one derivative of the metric. So the divergence introduces another, and then we've got this v derivative. So if we had a k-squared term, we'd get 3 derivative terms on the left-hand side. But the Gauss-Bonnet term famously doesn't generate terms with more than 2 derivatives in the equations of motion. And so that's, I think, a heuristic way of understanding why you don't get those terms for Gauss-Bonnet. Yeah.
Perhaps a very naive question. So I saw that the cosmological constant doesn't play a role in that, right? The sign.
Mm-hmm.
So would it make sense to apply this to cosmological horizon?
So we've always got this assumption that we're working perturbatively around a stationary black hole. If you had a cosmological horizon, it's less clear to me what you would be doing there. Yeah, I don't think you'd have this structure that you have around a stationary black hole. It's an interesting question that we haven't thought about. I mean, this equation we derive here, this is completely general. This applies on any null hypersurface. So, yeah, it would be an interesting question to investigate what the implications of this equation for a cosmological horizon. Okay, so, but what the result of that investigation would be, I don't know.
But definitely holds for the seated black hole, let's say. So.
It definitely holds for black holes which are settling down to equilibrium at late time.
So the result that you have the algorithm for it applies to stationary black holes?
No, so Wall told us the answer for stationary black holes. Aron Wall gives us an answer that holds for linear perturbations of stationary black holes, and our result now gives an answer which holds to quadratic order in perturbations around stationary black holes.
So your result will just reduce to the Aron Wall in the case where there's no time dependence?
Yeah, exactly, yeah. So without time dependence, everything just reduces to the Wald entropy, yeah. And to linear order, it's the same as the Aron Wall entropy.
Yeah, is there some meaningful notion of temperature in these out-of-equilibrium situations?
And that's there's something people have thought about. I'm not sure there's I mean, you could ask that even for standard GR, independently of any of this higher derivative stuff. And so, of course, the Hawking temperature is related to the surface gravity. So one thing you might try is to generalize the notion of surface gravity away from a time-independent situation. And so various people have tried to do that, but it's very classical, and I don't think there's any quantum calculation on that goes beyond. Well, the name tells us that that's related to anything resembling a temperature. So, yeah, it sounds tricky. Yeah.
Statistical ensemble is not equilibrium. What's a good measurement?
Well, that's you tell me. I mean, as I said, it's a difficult problem, right? This whole definition of entropy involves things like, so in fluid mechanics, for example, there's all these issues of coarse graining and so on, and
Mm-hmm.
There's still a notion of
Number of states.
yeah. But you have to ask the number of states satisfying what properties. So you're always, when you're talking about entropy, you're always conditioning on some macroscopic observables, right? So you have to say what macroscopic observables do you want to fix in order to do your counting, yeah. And then I think you start getting into issues of coarse graining and so on, and it gets kind of murky.
To go back to the Einstein gravity time-dependent case, there could be a thousand horizons, horizons defined with different properties. Is there anything in a sense different or new that you can tell us about this case?
We haven't thought about it, to be honest. Yeah, I mean, because our focus is mainly on understanding higher derivatives. We did have some discussions with Bob Wald about this, and he has some stuff that he says leads to some new notions of entropy for Einstein gravity. But again, in this perturbative setting that we're discussing. So, maybe I'll say one more thing about Einstein gravity, which relates to this issue of field redefinition. So I said that for Einstein gravity, our result just gives you the area, which it does if you just take Einstein gravity and apply our method. But if you start with Einstein gravity, perform a field redefinition to introduce R squared terms, and then apply our methods, you don't get the usual entropy. And so in that sense, we give you an entropy for Einstein gravity, which is not just the area, it's the area plus some other stuff. Okay.
Is the notion of adiabatic variation somehow built into this approximation?
I'm not sure what adiabatic compared to what. I mean, we're always assuming that things are slowly varying compared to this UV length scale. So we're within the regime of validity of effective field theory. But I mean, you could ask. So for example, one thing you could ask about is how does this differ from what people do in fluid gravity? So in fluid gravity, you have another scale which is defined by the temperature, and you're kind of looking at things which are long wavelength on that scale. That's much longer wavelength than we're looking at. So you could. Yeah, if you were to build fluid gravity on top of this, then it would introduce another kind of slow variation, which would then lead to a more refined expansion of more refined formulae for the entropy, I guess, in terms of quantities which are only defined in that very long wavelength limit.
For instance, you could imagine the temperature itself being slow.
Yeah, so that's essentially what people are doing in fluid gravity, isn't it? Yeah. But of course, all of this applies there to a much wider. The regime of validity of what we're doing is much broader than fluid gravity.
Okay, I think it's time to break for lunch. Let's try.